All right. Hello, everyone. Thank you for attending the CS201 Computer Science Department seminar. So today is our first seminar for this academic year, and it is my great pleasure to have Professor Michael Mahoney from Berkeley to speak and kick off the year of our seminar. So Michael has done a lot of landmark works in machine learning, optimization, and big data analytics, including randomized numerical linear algebra, second-order optimization method, and more recently, deep learning theory and algorithms. So before we start, I'd like to say something about the logistics of this seminar. So during the talk, if you want to ask questions, please just click the raise hand button on Zoom, and I will unmute you to let you interact with our speaker, Michael. And you can also type in your questions on the Q&A features on Zoom, and we will collect all those questions and let you ask those questions at the end of the talk. All right, so now let's welcome Michael to speak.
All right, well, thanks a lot, and thanks for the invitation. It's great to have the chance to tell you about some of the work we've been doing. As I was saying before we started recording, the only thing better than giving a seminar in this sort of online form is if I could head down there and visit for the day and do it in person. So maybe we'll have to do that next year, but given that that's not on the table right now, it's great to have the chance to tell you about some of the things we've been doing recently. And we've done work in from a couple different perspectives, and what I want to tell you about today is one aspect of it. So what I want to talk about today is a second order optimizer. So by second order, I mean I'm going beyond gradient information to include Hessian, second derivatives. So second order optimization has to do with Hessians and second derivatives. These are a set of techniques that are widely used in scientific computing. And they're obviously the right thing to do in scientific computing. And the sort of conventional wisdom recently in machine learning is they're obviously the wrong thing to do in machine learning. And so we're sort of pushing against that a little bit. And we're going to call this Adahesian for adaptive Hessian. There's going to be an adaptive step, and that'll be important. This is work with a bunch of people over the years. I have a student, Joey Yao, who's going to be finishing up in about a year. And a lot of this work was really led by a great postdoc, Amir Gulami. So mention them in particular. Follow up with me if there's any questions. Probably what I'll do is put you in contact with them because they're great and they've led the effort here, not just on this optimizer, but on a range of different things in terms of quantization and using second order information to get integer sort of optimizers and quantized versions of state-of-the-art models, BERT and very large scale computer vision models, not small little things. So we're really trying to push the limits on the applied side and come up with novel optimizers on the algorithmic side. So I wanted to give you a little bit of background just to provide a little bit more context for that. And I'm having a problem with my, oh, there I go. So a year ago, I gave a talk with the sort of immodest title, making the deep learning revolution practical through second order optimization. And the context here was that a lot of developments, I think, in machine learning and deep learning in particular are just deeply, deeply impractical. They're deeply impractical because the way models are parameterized and formulated typically involve gradient methods. You sort of roll downhill. Now, vanilla gradient methods, stochastic gradient methods, actually do not work so well. And so what happens is you come up with a gradient method prime and a gradient method double prime and triple prime. And so you come up with Adam and you get Adagrad and you get Adam W and you get something else, an SVRG, and it is a gazillion parameters, it's a gazillion acronyms, each one corresponding to a different, different way to combine first derivative information. And then you parameterize them and you hyperparameterize them. So now you have to determine lots and lots of hyperparameters. And this is extremely, extremely expensive. And so I forget the number. One of these models a year ago for some StarCraft video game or whatever, which was a state of the art, cost, I don't remember what it was, $100 million or some incredible number to develop a model. So that's not something that's going to be an option for not just most academic environments, all but a handful of companies. That's something that's just off the table. And so it's really a very impractical situation. And so the claim was going to be that second order methods really could address some of those problems. And it's not that I'm suggesting you go and you dust off a second order optimization book from your shelf and implement those algorithms. They tend not to do so well. What the claim is going to be is that if you take a step back and you ask, what are these second order sort of techniques designed to solve? What problems are they designed to solve? They're designed to solve a problem that there's not a natural step size in a first order algorithm. By natural step size, I mean, if you determine that there's a gradient, and gradients in high directions, derivatives in high directions are different than derivatives you learn in first year calculus, where it's a number, it's how much you're up or down. In high dimensions, really, it's a direction. And so you determine a direction, and then you have to determine how far to move in that direction. And there's no reason to move, large or small. I mean, theory says you anneal in some way, but the practice is very, very, very different than that. And so, people don't know to orders of magnitude.
Hi, Michael. So
Yeah.
have you switched your slide to the third one? So we are still on the second slide.
I'm on 1 year ago. Yeah.
Oh, okay, cool. Sorry.
Yeah. So this is, so people don't know how much to step. In second order methods, there's a natural step size. It's 1, and maybe you backtrack a little bit, but that's a much weaker sort of hyperparameter. And so you have to choose lots and lots of hyperparameters. So we wanted to make it practical, and the idea was we're going to use some we'd use optimizers. We could use it for quantization. There's a range of different things we would use these second order methods for. So the problems machine learners are having with lots and lots of hyperparameters. Something called exploding gradients and vanishing gradients, which numerical analysis would call bad conditioning. But exploding gradients and vanishing gradients sort of sounds more dramatic, and so people focus on that. So there's exploding gradients and vanishing gradients. Second order methods are designed to do that. You might call it a preconditioned first order method, but it's a second order method. It's using that sort of information. And so the conclusions we came to were that that a lot of these techniques really could work. The initial successes we had were in terms of analytics, in terms of sensitivity information, also in quantization. And we had a proof of principle about a year ago that it would work for good optimizers. And that's what I'll be talking about today. So that's 1 year ago. 3 years ago, so actually this work you heard, we had done work on randomized linear algebra. The background of this work, we actually came in on the theory side, and we had done scalable randomized linear algebra, subsampling for just basic matrix problems. And under the hood in second order algorithms, you got to solve a certain matrix problem. Naively, you'd invert a matrix. Naively, things do not work particularly well. So basically what you got to do is come up with an approximate linear system solve. And so all the efforts in terms of coming up with a smart linear system solve. And so we came at it from the perspective of scalable second order optimization algorithms. And so this is sort of how we came at it. And there we were asking sort of similar questions. And we really, flag and flare was a method we developed where we tried to come up with sort of the best of both worlds, methods that got acceleration, but also controlled the geometry, which if you're familiar with first order methods, those are two sort of types of improvements you can have. But it quickly became clear that there was just lots and lots of parameters that would enter here. And it really made sense to step back and say, we want to use second order methods more broadly defined, not just invert a Hessian. So, but a little bit more sophisticated way. So I want to give you the executive summary. Here's the bottom line. If you want to go home, well, you probably are home, but after this done, this will be the bottom line. And then I'll spend the next, however, 45 minutes, whatever, going through sort of in a little bit more detail what we're saying here. So the background was in randomized linear algebra and scalable second order theory. But we really want to solve very particular problems on the machine learning side, different than in scientific computing. And then we felt about a year ago confident enough that we could say, very practical problems that make a lot of gradient-based machine learning methods just deeply, deeply impractical for industrial AI and machine learning, for scientific AI and machine learning. These sort of second order methods could solve, and they could solve because they were designed to solve those problems, not that the way they were implemented in the past is the right way to do it now, but they were designed to solve poor conditioning and step sizes and hyperparameters and so on. So we're going to talk about training algorithms, and we're going to talk about Adahesian. And so Adahesian is going to be a novel second order optimizer, and it's going to achieve state of the art. It's going to achieve state of the art on a fairly wide range of tasks. There's going to be tasks for computer vision. There's going to be tasks for natural language processing. There's going to be tasks for recommendation systems. And essentially, it's going to achieve these by coming up with a low-cost Hessian approximation. It's going to be a diagonal approximation. It's going to be applicable across a fairly wide range of networks. We're going to make very weak assumptions on the architecture. Right? We're not going to over-optimize to computer vision and convolutions, to natural language and attention matrices. And, so we're adopting sort of a relatively agnostic area, and I'll say why in a minute, but relatively domain agnostic technique that'll instantiate itself in different ways depending on the area, but it should apply to all those areas. So low cost diagonal approximation to the Hessian, and then good algorithm engineering, good performance engineering. So a novel temporal and spatial smoothing, we got to block things off in the right way to take advantage of the cache structure and so on. But a novel temporal and spatial smoothing, which will help essentially reduce the variance and reduce the noise across iterations. So that's a summary. A second order optimizer that I think in a fairly strong sense of the word just is state of the art across a state of the art in computer vision, state of the art in NLP, state of the art in recommendation systems. And that's actually a rather strong claim because most first order methods apply to one of those areas and not one of the other areas. When I say that, I want you to pause for a second and think about what I mean by that. So choosing the right hyperparameters for optimizing a neural network really is a bit of a dark art. So I have on the right here some, middle-aged wizard or something. So it's really a dark art. There's a potion. You fiddle with this hyperparameter. You vary this value. And one magically works after you spend 1,000 million, however many dollars on CPU or GPU time. So problems. I mean, deeply impractical, brute force hyperparameter searching, which there's not guiding principles in terms of why these things should work. The theory, 99% of the theory makes essentially convex analysis assumptions, convex assumptions on smoothness properties, which it doesn't even provide qualitative guidance to how these things are used in sort of state-of-the-art machine learning. And by hyperparameters, I don't just mean step size and batch size and sort of all the usual things. Even the choice of the optimizer is a hyperparameter. So why would you use Sgd, maybe Sgd with momentum, in computer vision and not NLP? Well, why would you use AtomW in NLP and not recommendation systems? Well, why would you use Adagrad in recommendation systems and not computer vision? So these are all first order methods, so call it first order plus plus, where you include some momentum or you include some adaptive updates to something. And it really, I don't think a priori would have been obvious. There's no reason why one or the other should work in one area. I mean, they typically are proposed with some sort of plausible assumption. You say, well, I have some terms that are large, and I have some drag effect, and I have some convolutions that do something. But those really are retrodicting, right? They're sort of after the fact story. There's no reason why one method would perform well here versus another area. So if in addition to computer vision or NLP or recommendation systems, next year there's another killer application, not obvious that any of these would work. And if they don't, there's not obvious why there'd be sort of a guiding principle in how to engineer a first order method to do that. And so really the choice of the particular first order optimizer, I think, is becoming a knob to fiddle with. And I think this may not be obvious to you if you just do sort of popular things like ResNet 50 training on ImageNet. And the reason is that years and years of industrial scale, namely brute force hyperparameter searching, really has designed these such that Sgd methods perform well. So there's really hardware infrastructure, a software infrastructure that really provides a fairly strong bias to these sort of first order methods. And so that's something we really had to wrestle with when coming up with the state of the art sort of second order method with Adahesian. All right. So Sgd training. So, we have on the left here, sort of a lost surface. It goes up and down. For one dimension is extremely, extremely different than, 2 or 3 or 1 million dimensions. And so pictures like this are sort of very deceptive in a lot of ways, but put that here. Nonetheless, we have an objective, minimize some energy or some loss. It's a sum over n data points, something like empirical risk minimization, a sum over n data points of a cost. And the way you do it is you have a state and you compute essentially a derivative and you update based on some step size and step length. Empirical fact, it may not be obvious, but if you look at, pull out one, but these layers are very different. In some cases, think of it like a quadratic function. The quadratic function has a bowl, y is equal to alpha x squared. In some cases, that alpha is 1. In some cases, it's 10. In some cases, it's 0.1. The curvature properties of these are actually very different. And that's going to be key to second order methods. So this is sort of vanilla Sgd based training. a general update formula for, let's call it first and second order methods, but a general update formula for first order methods in particular is that the weights you have at time t plus 1 equals the weights at times t plus eta. Eta is going to be a step size. With, ideally it's, if with say second order methods, it's 1 and then you backtrack a little bit. For first order methods, it's just a parameter to fiddle with, and you typically don't know it to orders of magnitude, and it's extremely sensitive. If you anneal in one way, you get some convergence rate theory. That's not at all what people do. People keep it flat and then jump it down. So, the parameters at t plus 1 is equal to the parameters of the previous step plus a delta, change with times the step size. And so the way you should think of first order methods and second order methods is that the delta W, not the magnitude, but the direction you take, is either the gradient, meaning you choose the gradient direction, maybe a stochastic estimate with SGD, but stochastic estimate of the gradient direction. And then you move in that direction some step size eta. Or you say there's a gradient direction, but I'm going to take into account the curvature. In one dimension, the curvature looks like this, the red and the blue and the green. But in 2 dimensions, it looks like a bowl, a mountain valley where there's some long axes and some short axes. In a million dimensions, it's a more complicated version of that. And if you're not in a convex region of the landscape, there's some dimensions pointing up and some pointing down and a lot that are flat. And so in that case, what you do, and I hesitate even to write inverse Hessian, because if someone says to use second order methods, you need to invert a Hessian, you should hang up on them and go home. So you don't have to invert a Hessian, but I'll write it down formally, that you have a Hessian inverse times a gradient. Namely, you choose the stochastic estimate of the gradient, and if you think of this in terms of its eigendecomposition, you rotate, you stretch, and you rotate back, and that's the direction you take. And in that case, the step size is usually 1, and then you backtrack a little bit to figure out the right step size. So in both cases, you have a direction, and there's actually a spectrum here. You could imagine taking the Hessian to some power, and so the picture you should have in your mind is that if you start out here, well away from, this is a nice quadratic function. With a quadratic function, the second order method will optimize it in one step, but leave that aside. This is sort of the right direction. And so gradient descent or a momentum-based variant of stochastic gradient descent, very easy to overshoot this nice little basin here, unless you choose the parameters exactly right. And so it's going to be much easier with a second order method. And so that's going to be the key point. I just changed the parameters here on you, sorry, from W at the next step is equal to W at the current step minus eta delta W. Change that to thetas, but they're the same. So the parameter at time t plus 1 is equal to parameter at time t minus this eta step size times the delta. Think of the update as Hessian to the 0 power, namely the identity times the gradient, or Hessian to the -1 power times the gradient. So you solve a linear equation solve. Hessian times delta theta is equal to g. And you can ask, what about the middle part? And one of the knobs that is suboptimal for convex optimization, but that's important here, is you may want to not move as aggressively, rescale as aggressively as the full inverse Hessian. You might want to choose Hessian to the -½ power. And so that's something we actually did. So let's say that instead of using the full Hessian, we're going to use a mixture form of it. So instead of using a fully first or fully second order method, let's use Hessian to the ½ power. This is a knob you could fiddle with. We just chose a half because it was easy. I mean, you could optimize that, but for convex problems, this will be a descent direction, which these problems are not. For simple problems, you can do this. Compute the Hessian inverse, Hessian to the -½ power. Basically, you're not stepping as aggressively, or scaling as aggressively. For large-scale problems, you can't do this. And you can't do this for a couple reasons. I mean, even dealing with never mind inverting the Hessian, even writing it down is impractical. You can't. So you should think of, you have 10 million parameters or some number of parameters. Gradients are size 10 million. And that's something you can store. 10 billion, 100 billion, it starts to get to be hard. But 10 million you can easily store, right? So you can compute a gradient. A Hessian is size 10 million squared, or 10 million choose 2. That's much less, you're much less able to solve it. But you should ask yourself, think like a statistician might be. If you have 10 million, maybe times 10 or 100 bits of information from that, do you really have 10 million choose 2 bits of information in the Hessian? I mean, are all these things really that meaningful? Or is there probably a lot of noise off diagonal here you're fitting? And since it's well known that estimating sort of Hessians is going to be a lot harder for that reason in statistical senses. When you do optimization, convex optimization in scientific computing, you're typically working with a data set in front of you. And so the understanding of the noise properties of the data usually is sort of exogenous to the optimization algorithm. Here in ML, it's usually parameterized as you're doing a stochastic optimization because of an empirical risk minimization. But the empirical risk minimization is only a proxy for what you really want to do. You want to optimize the true risk. And so you should think about being a little bit more cavalier about these off-diagonal entries. And so, you know, they may not be so meaningful to make update decisions based on, and we'll get back to how we actually exploit that in a moment. So that's the second derivative of the Hessian. Looking inside the black box of what's going on, let's say you have a couple layers, layer 1, you know, to layer n. I did a cube here. It could be in other models that doesn't have that sort of structure. But what you see in a lot of cases is that if you look at the loss landscape, depending on the relative eigenvalues of this Hessian, that'll say sort of how curved this loss landscape is. So, you know, in some cases, this is pretty flat. In some cases, this is pretty choppy, you know, pretty steep. And gradient information will tell you which direction to go in, but the Hessian information will tell you something about the curvature properties of this, which varies fairly non-uniformly across different layers. So the other work that I alluded to before on quantizing basically says, you know, you should quantize different layers, different amounts depending on the curvature properties. If you're familiar with like stiff differential equations, there's 2 different time scales going on. You hear that here at different layers, there's different curvature scales going on, and that's important for the quantization work. And it's also going to be important here for the iterative algorithm, the optimizer that we have here.
So how do you visualize the loss landscape in this figure?
Yeah, these we choose a few of these particular ones. I think we chose them randomly, or you choose the top 2 eigenvectors and you plot it here. So we're plotting, you know, 1 million dimensions on 2 dimensions here. So okay. This is a suggestive picture that, if you're familiar with visualizations, you know, is hides as much as it reveals. But in this case, we plot this on the top few eigenvectors.
Okay, thanks.
In this case, the suggestion that the pictures would suggest is in fact the case. I mean, we can easily find examples where it looks one way, but really the properties are something different. You know, you have a bunch of negative eigenvalues, some very large ones. I mean, some other things that get funky for various reasons. But in this case, it's you know, we're not cheating on you. All right. So what we want to do here, so we want to get second order information. And one thing people do is low rank approximations to the Hessian. That's actually with the way we came at this when we were doing, came at this from randomized linear algebra. You know, we basically subsampled the Hessian in outer product form and got an approximation to it. I'm going to do something a little bit different here. And the motivation is that never mind, you know, solving the linear equation and inverting it, even forming the Hessian is intractable. We don't have 10 million choose, you know, we don't have memory to choose 10 million choose 2 parameters. Here I say 24 million, so 24 million squared parameters. So even forming the Hessian is going to be infeasible. And so we want to approximate it. In particular, we're going to take advantage of the fact that we think that a lot of this off-diagonal information is going to be pretty noisy. And so we're going to use a Hessian, we're going to use a diagonal approximation of the Hessian. You could have block structure, k-fac, other things. I mean, methods have come up with various forms of block structure to approximate off diagonals. We did work a few years ago on that, and looking at the scaling as a function of batch size and a range of other methods, we found that it's comparably finicky to Sgd. In certain regimes, it captures second order information. In other regimes of parameters, and it can be very not obvious to the user when this is happening, it really isn't a second order method. It's you know, it's a first order method essentially. And we found that in terms of fiddling with hyperparameters or looking at the scaling process as a function of batch size, it behaved operationally a lot like a first order method. And so, but you could put block sizes here, and people have done that with k-fac or other methods if you like to put off diagonal blocks. But we're working with a diagonal approximation of the Hessian. And the idea might be, if we're going to lose a little bit of information, if this was a one-off solve, we'd have to get the off diagonal information. But this is really an iterative algorithm. And so if we get the diagonal right, in the next step, we might pick up something if we fail to get it off diagonal. So we're going to work with a diagonal approximation of the Hessian. So I have an expression here that will subsume a bunch of first-order algorithms and a bunch of second-order algorithms, and I think it's on the next slide. So the Adahesian algorithm is going to be very simple, and it's going to be the following: that the weight at time t plus 1 is equal to the weight at time t plus eta, a step size, plus an m parameter divided by v. And I'll put on the next slide what these m's and v's means. But it's something, beta is a parameter, it's a running sum of something divided by that parameter. So these are very simple to compute things. And this will be the basic structure of a Hessian approximation. Now, the reason we're doing this has to do with the fact that a lot of hardware and a lot of sort of software systems design decisions are biased towards first order methods. So we wanted a method that looked sort of looked like a first order method, from the implementation point of view, meaning I can give you a vector, it's a gradient. I can give you a vector, it's the diagonal of a Hessian. I can choose these various parameter values, and it sort of looks like a first order method. I don't want to claim that this is the best. And in fact, if you had different hardware infrastructure, different software systems, there may be a better method. But given the fact that there's a lot of bias towards gradient-based methods, we structure the second order approximation that way. And so the next slide will show if you have an update of weights that is weights time t plus 1 is equal to weights at times t plus a step size m divided by v. SGD with momentum, here's your value of m and v. V is 1, so you have nothing in the denominator, which is why you might not recognize it. Where the m is m at t plus 1 plus a gradient. So there's a bit of a drag there. Adagrad chooses the gradient. You don't have the two terms here, plus a GG transpose, GG times itself, running total of that. So that's Adagrad. Adam has a bit of both. Adam has a running total here. It has a running total, slightly more complicated version of V here. So the point is that even the choice of the first order optimizer is a hyperparameter, right? Certain areas SGD is much better, other areas Adagrad is much better, other areas Adam is much better, or Adam W is much better. RMS prop, but they all have this syntactic form. And so at a Hessian, if you take a diagonal estimate rather than estimate of the gradient and other things, we have a gradient estimate of the gradient here also. But if you take a diagonal estimate D is the diagonal of your Hessian. We'll tell you how to compute that in a second, but it's the diagonal of your Hessian. You can just plug it into this form. And so really it's a relatively minor change if you're familiar with TensorFlow or PyTorch or these sorts of things. All right, so these are different optimizers. Now, how do you get the Hessian diagonal? All right, so computing H inverse, is that practical? People ask. And the answer is of course not. You can't even form H, never mind compute H inverse. But you don't need H inverse, right? Remember what you need. You need H inverse times the gradient. So if you can come up with an estimate for H inverse times the gradient, you never need H inverse. So we're not going to compute H. We're not going to store H. We'll use essentially what's called matrix-free methods to not approximate H inverse, but approximate H inverse times the gradient. That's basically the way we'll do it. And we're going to use ideas from randomized numerical linear algebra. And so there's a range of techniques here. And this is most closely related to the Hutchinson method, if you're familiar with that. So that's a method to get at eigenvector information without forming the explicit eigenvalue decomposition. And I think I have it on the next slide too. So if I was to write down H, what I want is the diagonal. And I can say that that's approximately equal to a random vector. Let's say Z is a random plus minus 1 vector times H. Now, a random vector times a big matrix is a vector. So if I have a way to evaluate this efficiently, I never need to form H. I just need to form the thing that's size n, size 10 million, let's say. And then I would do an element-wise product, and then I get another vector out. And this element-wise product turns out to be a good estimator of the diagonal of the Hessian. So I'm going to take a random vector, I'm going to dot it into H, which I'm not going to form. I'll tell you how to do that in a minute. And then I do an element-wise product, and that gives me a vector that is a good approximation to the diagonal of H. And that's what I want. That's what I'm going to feed into this step right here. So how do I do that? So how to compute the diagonal of the Hessian. So we take advantage of the fact, remember, I need to compute H times a random vector. So to compute h times a random vector, run through these two lines, what I can do is I can say, listen, say that I had a gradient and I dot that gradient into a random vector and I differentiate that with respect to the parameters. Right, so this z is the same as this z. So I'm looking at Hessian times a random vector. Let's say I dot that into the gradient. If I dot that into the gradient and take the derivative with respect to the parameters, chain rule gives me derivative of the gradient with respect to the parameters times z times gradient times the derivative of the parameters with respect to z. These are IID entries, and so in expectation, which of these? This will drop out, and so what we'll get is dg, d theta. The derivative of the gradient is just the Hessian times z. So this is sort of the key trick. It's the Hutchinson. It's related to the Hutchinson method, and so you use basically an implicit solve. Now, to get this matrix vector multiply, essentially we're going to have to do two gradient steps, two back propagation steps. So at worst, this is going to be 2x back prop time. It's in fact a little bit better, but we can get Hessian information in 2x back prop time. We can get all sorts of Hessian information. Here we're getting the diagonal. We can get the diagonal dotted into, some arbitrary vector if you want that. You can get other properties of the diagonal like the trace with a stochastic Langso sort of method. So not Adahesian, which is built on something called pi Hessian we have, but pi Hessian, which is a related code base. You can use a stochastic Langsos method to get the full eigenvalue distribution of the Hessian. So the full ESD. So you can get all sorts of Hessian information in only slightly more than gradient time. Let's say 2x gradient time, and we'll get back to, in fact, it's not that bad. And the key idea is use sort of basic stuff from randomized linear algebra. All right, so the basic Adahesian algorithm is going to be very simple. So this is the expressions we had a few slides ago. The idea you want to have in your mind is that we're going to get a better estimate of the direction you should be moving in. Maybe you're going to be able to bounce over little bumps in sort of the loss surface, but in a much finer scale way than you would with gradient noise. You may have to add a lot of noise, and that's going to adjust the surface quite a bit. So the basic structures are going to be very simple. Now what you see is noise on the scale of the blue here, or noise on the scale of the blue here. So this works, but you have a little bit more variance than you'd like. So to remove the variance, because we're using these algorithms for randomized linear algebra, so they either work in expectation or work something to close.
So we got a question from the audience.
Question.
Yeah. Hi, Professor. So I wonder how many Z samples did you use for each diagonal Hessian computation?
Oh, I don't know. How many these samples? So I don't know offhand. You're asking about this vector. I mean, this is a plus minus one vector, or chosen some other. So this is size. This is size n. This is size matrix. You could do other things, but in the simplest case, this is a plus minus one. They could be Gaussian, but generating the Gaussian variables is more expensive. This is a plus minus one vector of length n, or whatever the dimension is. So the simplest way to implement is just to do that. Is that what you're asking?
I mean, in this expectation of Z
right.
formula, did you use only one Z sample or use multiple of them?
Yeah. So I don't know. I don't remember the exact number, so I don't know that offhand. But we can look in the code. We chose some number, 10. I don't know, something modest. But we got blue. We got error at this size scale, and so the variance was this size scale. So it had some level of variance. If we increased it a factor of 10, the variance decreased by a factor of 3, but it was still sort of too large. So I don't know the number offhand, but we did other things to drive the variance down, which is why I don't know offhand. So we chose some default value, 10 or something like that. But then we drove the variance down. So I'll talk about on this slide and the next slide.
Cool.
So theory would suggest, that the main control parameters which you're suggesting, just choose more dot products to drive the variance down. And so this is one of the things that if you formulate theory sort of in a one-off way, that's the main control parameter, and you'd choose, 10 or 100 of these, and your estimate would have small variance. When you use this in other ways, as a practical matter, there's various ways to control variance that are better, and so this will be two of them. And so this is, slight theory practice gap. So what we're going to do is incorporate spatial averaging. So there'll be two different ways that we do this. But one is going to be to incorporate spatial averaging to smooth out the stochastic Hessian noise across different iterations. So this can take a couple different forms. So depending on the architecture or the domain, you average in certain ways. So you average in a way that sort of respects a convolutional block. Or if you're dealing with NLP, average in a way that respects sort of a multi-head attention block. So if you average that way, and nothing particularly fancy here, then you'll decrease the noise. And I don't know, look at the y-axis here. This is a factor of, maybe not 10, but well more than 3, right? So decrease the noise quite a bit. And so that decreases the noise and smooths out the stochastic Hessian estimator. So where this enters is, remember, you rotate, you rescale, you rotate. So how much do you rescale? If we don't rescale the right amount, this will be a little bit too choppy. And so, but we're already, remember how I said we're interpolating between first and second order, because we were choosing the square root of the Hessian. So if these are a little bit off, that's okay, because this is an iterative algorithm and that'll correct for that. So that's a spatial smoothing is one thing we do. We also do a variance reduction, and we just took the idea from first order methods that variance reduced. Here we have, your M term and your update equation has the gradients in it, the running total of the gradients of the last t steps here. And the V term has the diagonals. First order methods would use the gradient here. We have the diagonals of the Hessian. And just use momentum to smooth that out. So we haven't developed the theory, but the theory would be basically the same as first order sort of momentum methods, but it would smooth this out. And so that's a second way that we reduce the variance. So here's the basic algorithm, initial parameter, learning rate. So if no one had ever developed first order methods, we actually have a lot of things to determine here, right? An initial parameter, a learning rate, a couple decay rates, block size, Hessian power, and so on and so forth. Fortunately, people have developed first order methods. And so essentially all these parameters, except 2, we're just going to be able to choose to be fixed and optimize just 2. And so we're going to have essentially many fewer parameters to fiddle with when we did our parameter searches, and still achieve state of the art. So I'll get back to that in a minute. So set your initial gradients and diagonal approximation of the Hessian to 0 for time is equal to 1, 2, 3. Here's your current gradient estimate. Here's your current diagonal Hessian estimate of the Hessian of the diagonal, and update M and V in equation 10, which was that basic equation we had a few slides ago, and update the parameters. And this is the expression I had before. All right. So this is the basic algorithm. A lot of implementation details to really get it right, but this is the basic algorithm. But we were forced ourselves to feed this through the infrastructure that was really biased towards first order methods. So important points for the empirical results that I want to walk through. What hyperparameters do we modify? So we modified a learning rate. We didn't have a learning rate decay. We modified a fixed learning rate, and we modified the spatial averaging block size. Oops. So when I said we did spatial averaging, how wide is this block? We average that. So this is how denoised is this step. So we treated that as a parameter to modify. Things that we did not modify in the empirical results, I'll show you. The learning rate schedule, we didn't touch that. Weight decay, we didn't touch that. Warm-up schedule, we didn't touch that. Dropout rate, we didn't touch that. First and second order momentum coefficients, beta 1 and beta 2, we didn't touch that. The particular first order method, which as I said is a hyperparameter, we didn't touch that. We just have one basic equation that we had there. We didn't have 3 or 4 different ones. So you could fiddle with these things if you wanted to, and you could probably do marginally better than the results I'll show you. It would take a factor of 100x, 1000x compute time, 10,000x compute time, but you could do that. But we weren't interested in that. We just wanted to beat state of the art with something marginally more expensive or comparable or slightly less expensive to the final step of usual first order methods. So these are the things we fiddled with, just the fixed learning rate and the spatial averaging block. All right, so I want to show you some results on image class from computer vision on images, natural language processing recommendation systems. And in each case, we're going to compare to the best first order method, but the best first order method is different between the 3. And in each case, we're going to compare to add a Hessian with just those 2 parameters that we fiddled with. So here we're going to look on image classification, CFAR and ImageNet, ResNet 20 and 32 and 18. Here we're going to compare against Sgd and let's say Adam and Adam W. So a few things to note here. Here Sgd is the best on 32. Adahesians, so higher is better on this metric. This is whatever error or quality. So higher is better. Sgd, let's say 92 versus 90 versus 91. So this is actually a big difference by the standards of the area. So 90 is a lot less than 92 by the standards of the area. 64 is a lot less than 70 by the standards of the area. So Sgd is the best here. Adam and Adam W are quite a bit worse. Adahesian is the same. So 92.08 versus 92.13. It's a little bit better here. 93.14 versus 93.08, marginally worse here. So, but they're the same. 70.08 versus 70.03, right? I mean, if you were to run this different times, whatever, these are basically the same. So Adahesian's the same or marginally better than Sgd with momentum, but quite a bit better than Adam and Adam W. So this is a basic image classification task. Let's look at machine translation. So higher blue scores here are better. Higher is better. Here, Sgd really does terribly. 28 is much worse than 35. Adam is the state of the art here. Sorry, Adam W. 35. 28 is much better than 32. Adahesian straight away is comparable, slightly better than, but comparable to Adam W. In both cases. So this is a machine. This is the state of the art machine translation problem. Results for language modeling. Similar here. We're dealing with perplexity. Lower perplexity is better. Adam W's 54 compared to 59. Adahesian's, well, here it's quite a bit better actually. 20 much better. I mean, Sgd is terrible here on the Wikitext 103 problem. Adam W is 20. Adahesian's 19.9. So squeeze Bert on glue. Here, these are accuracy. Higher accuracy is better. The first line here is what we got from the paper. The second line is we reproduce their results. 1 or 2 higher is better. So 1 or 2 were a little bit better, but than what they had actually. But in essentially every case, we were able to reproduce their results. Adahesian was better on 5 of the 8, but comparable on all of them. So comparable with state of the art on every one of those. So results on recommendation systems. Here, this is test accuracy, and this was comparable to Adagrad. So Sgd, I don't even have the results here for Sgd and Adam, which were much worse. So Adagrad was the state of the art here. Adahesian is comparable, slightly better. So computer vision, NLP, and recommendation systems with fiddling just the 2 knobs, not all those complicated equations, 3 different optimizers, lots of other stuff. We were able to match every one of those 3 without extensive hyperparameter tuning that way. So I want to talk about the speed comparison. So an important advantage of Adahesian is not just that it achieves state of the art, but its per iteration cost is comparable to Sgd. So I showed you that equation, the Hutchinson thing, and I said the runtime should be something like twice as much. And basically it's because we fed the second order optimizer into the software and hardware infrastructure that's being designed for first order methods. And we need to do 2 backprops. And so it's theoretically, it's 2x. It's in fact about, I don't know, I have a 3.2 there. It's about 2.4x. And that has to do probably with just some second order, well, no pun intended, second order bits, low, finer scale things that provide a little bit of a bias towards first order methods. So it's, 2x worse. That's if you do the Hessian computation every step. If you do this approximate solve every 2 steps or every 3 steps or every 5 steps, the quality, 92.13, 92.4, 92.06, 92.17, 92.16, the quality doesn't change at all. It's at the error bar level. And now the cost is 1.25. You could push this out a little bit more before it starts to get a little bit worse. So I said 2x. In fact, it's 1.2x or less. So the cost for not doing Hessian information is that 1.2x. In fact, it's better than that because this is just comparing the very last computation, not all the computation time it took to come up with the hyperparameter sweeps and the expensive computation there. So it's hard to come up with a fair comparison. The best I can come up with is we had something a couple years ago where we were comparing with what our not extremely modest compute budget could do to look at scaling as a function of batch size, SGD, and KFAC, and a range of other methods. And we came to a bunch of results, and we got fairly choppy curves. And about a month later, Google came out with much smoother curves, and we estimate that they computed, their compute budget was 10,000 XRs or something like that. So, if you're gonna, I think it's a good question to say, given Adahesian, what's the right way to design a fair comparison to say, not just the final step, but the full cost of hyperparameter sweeps and so on. So let's just pull a number out of there and say it's 10,000. So now we're saying, well, it's the backprop is 2x more, but we're a factor of 10,000 better on the computation time to do the hyperparameter sweep. So really, we're only a factor of 5,000 better. So I think for a wide range of use cases, that's really the pain point, is these hyperparameter sweeps. It's not the very last computation on the last model. So that's the speed comparison with SGD methods. Robustness to hyperparameter tuning. For a fairly wide range of things, we saw that we're much more robust to hyperparameter tuning, and we're also more robust in a way where we fail gracefully. So as an engineering principle, you don't want to be fine, and then fail ungracefully. And if you look at Adam W, as you vary the learning rate, you're fine, you're slightly better, slightly worse, and then boom, you hit a wall and you die. Here, over a much wider range, with Adahesian, you're robust to hyperparameter tuning. And so I think that's going to be a more general phenomenon also. This is a particular example. I think that's more true more generally. Robustness to spatial averaging. Similarly, you get, the best results in the thing I showed you was that, when you average over 32, but if you average over 16 or 64, 128 or 8, you get results that aren't dramatically worse. So you're fairly robust, and this corresponds exactly to how good is your estimate of the directions. And so if you misestimate the amount that you stretch the directions, you can correct that in the next step. So it's not like the end of the world if you don't do that. There's just a lot of related work. So in the last just couple of minutes, let me sort of summarize the related work. Lots of benefits of first order methods, but in practice, they're really very brittle. And I think a lot of machine learners, the mental model they have is that first order, the mental model of first order methods is a nice one. Hessian and second order is a little bit more complicated, so don't go there. And just have first order prime, first order double prime, smooth, add adaptive gradients and this and that. And when you make all those corrections, you get methods that are very brittle, and it's very easy to solve poorly posed problems. And so therefore you have all sorts of problems with adversarial training and backdoor attacks and so on. Second order methods have been explored extensively in scientific computing. There was early work actually in ML on second order methods, and then they fell out of favor. And now just within the last 5 years, a lot of this was actually started by Fred Rooster, who was a postdoc with me about 5 years ago, and sort of led the charge on the theory front. And then Amir Gulami on this implementation work. And so there's now papers out there, second order made practical and Adahesian, so a range of things. People have looked at a lot, and I think whether you call LBFGS a second order method or not, I don't know. That's a matter of where you want to draw a line. But I think that the corrections that people are doing to first order method with these hyperparameters in a way that's very brittle, the problems they're trying to solve are the problems that second order methods are designed to solve: poor conditioning, and appropriate step sizes, and having fewer parameters. So so second order methods are trying to solve these problems. They just do it in a much cleaner way. And we were talking about this for a while, and people said, well, if it really works, why don't you come up with a better optimizer? So we did. So this is sort of Adahesian. So this is Adahesian. I wanted to just mention some related work on Pi-Hessian. I mentioned this before. This actually predated Adahesian by about 6 months. Pi-Hessian, the Pi is Python and the Hessian is the Hessian. And it's a package that just computes lots of stuff. It computes the largest entry with essentially a power method. It computes the trace and a range of other things with essentially this variant of the Hutchinson method I talked about. It can get the full Hessian empirical spectral distribution with the stochastic long cells. And we use that not inside this optimizer, although we use similar ideas, but we used it for quantization with Hawk and Qbert and inference. And we've also used it for model validation, looking at the loss landscape and model robustness, properties of adversarial data and backdoor data, and just to test hypotheses. There's lots and lots of things people say in ML, and they're not really formulated in a way where they make a testable statement. So is the loss landscape smoother? You know, when you train, do you come to a minimum? And the answer in a lot of cases is just no. You're trained until you get tired and then you stop. And so you can test hypotheses about what's going on with this. And again, it takes 2x, gradient time, which, if you're not willing to pay that, so it's certainly not, much more expensive than first order methods. So with that, let me put up the slide I put up at the very beginning, which just sort of gives the executive summary. So Adahesian is a sort of a second order optimizer, uses ideas from second order optimization, grew out of strong theory practice gap. We had to come up with a bunch of sort of performance engineering enhancements. Some of them, I think, are going to lead to nice theoretical questions, because the theory, the way it's formulated in terms of arbitrary surfaces or nice convex, I mean, there's a big gap. And I think some of the insights we have here will feed back to that in sort of very nice ways. But it also shows you how to go beyond just designing software systems that are good for gradients, where you can do sort of more intelligent and more careful stuff, I think. It achieves state-of-the-art on computer vision, NLP, and recommendation systems. I'll say almost out of the box with very little hyperparameter fiddling. Whereas first order methods, you have 3 totally different methods that achieve state-of-the-art in each of those areas. And it does it with the diagonal Hessian approximation, some spatial and temporal smoothing that required a lot of care in terms of software coding, but it's relatively straightforward. And so go home, try and break it, get it to work, and test hypotheses, come up with more robust algorithms, more robust models, and let us know how it goes. So with that, let me wrap up, and if there's any questions, I'm glad to hang around a little bit and answer some questions.
Thank you for the great talk. Yeah, thank you. So yeah, we do have some questions from the audience. So let me, okay. Yeah. All right, so go ahead. Hello?
I don't hear anything.
Yeah, I don't hear. So you can start to ask question.
Hello?
Okay, yeah, I can hear you.
Oh, okay, sorry. There's something wrong with my Zoom app. So I have a question about the idea of interpolating the first order and second order methods. So is there any particular reason you choose to kind of relax the power of the Hessian? For example, what if we kind of do some kind of linear combination?
This is one of these. So in a bunch of cases, when we worked with stochastic estimators, in particular coming out of randomized linear algebra, people would want to sample with respect to quantities, non-uniform quantities, and leverage scores, for example, or something like that. And when you sample with respect to them, to get estimators to work out, you had to have 1 over them in the denominator. And oftentimes focusing too much on them meant, you might get a good result in theory and in worst case, but you maybe fit too much to those things, because when you put the inverse of them on the diagonal, estimators would get bad, or the variance would get bad or something. And so when we were looking at this, we saw that in some cases, using the full inverse Hessian, because you're going to have small eigenvalues and they'll flatten out. And not that we were using the inverse Hessian, but we were computing the linear equations. When you did that, then we saw sort of analogous results. So we don't have a strong theoretical understanding of that, but we saw sort of similar situations where you might have been sort of overfitting to the fact that you should stretch out more along these directions, where in fact you should essentially shrink them a little bit in statistical language, maybe come up with a shrinked estimator. So the idea was that we have an estimate for the Hessian directions. The small ones, maybe want to shrink them a little bit, or shrink the spectral range a little bit. And so one way to do that was to come up with this power. I mean, I don't think a linear combination, well, depending on how it's implemented, a linear combination of the two might be good, but it was more like a shrinked estimator of that. So I mean, you could probably implement that in other ways, in particular, if you wanted.
Thank you very much. So, can I ask another question?
Yep.
Oh yeah. Thanks. So, like, what's probably the empirically, what's the best choice of the k parameter, or is it kind of various?
K meaning the interpolating between 0 and 1.
Yes.
You know, we took it. We chose a half, and we didn't want to fiddle too much. I suspect it would be pretty robust, and I suspect that because you know this is not a one. I mean, this is not a one-off computation. This is an iterative computation, and so if you chose it a little bit off, you know, you'd be able to correct it at a later step. So we didn't explore that extensively, partly because we wanted to come up with something that sort of worked across a range of areas, and I suspect the optimal one may depend on the particular area if you really wanted to squeeze that hard. But so we didn't explore that too much.
Thank you very much.
Yeah, so the idea is we wanted to come up with not a first order plus plus, where your mental model was first order, and then add bells and whistles and hyperparameters and so on to combine them. We wanted the mental model to be second order and then back off a little bit and say, well, you know, if you're really doing second order, in some sense, you're overfitting this, back off a little bit. Because a lot of the first order methods, momentum thing, can be viewed from the second order perspective. But, you know, if we made the Hessian the primary object, the Hessian the first class citizen, and said, well, you know, let's come up with a method that's second order minus minus, you know, back off that a little bit, but do it in a way that sort of conforms with the natural structure of it, right? So rotate, stretch a slightly different way, and rotate back the way the inverse Hessian would. So that's sort of the way we were thinking about it.
Yeah, so we have another question. So Adahesian, you can unmute yourself.
Yeah, hi. So how does this method compare to methods like KFAC or maybe Lisa?
You know, we looked at a range of methods before that, and, you know, prove me wrong, but I think this is, if you want to do state of the art, I think this is just going to be better than them, both in terms of the single training as well as robustness to hyperparameters and a range of other things. I mean, in particular, we spent a bunch of time with things like, I mean, you know, I don't know what it means to be a second order method, right? People, and I think that maybe because it was one of the ones earlier on, gets a lot of attention. But in terms of one of the primary things we've been worried about, which is these robustness to hyperparameters, it really behaves a lot more like a heavily hyperparameterized first order method. And you oftentimes fail to get lots of fine scale, you know, structural insights that second order methods would give you. So I think Adahesians is sitting on top of pi Hessian, which is a way to extract the fairly fine scale spectral insight and bias towards the diagonal. So I think that's the sort of thing I can imagine people say, well, there's off diagonal information and so you shouldn't do that. But there's just, you know, there's 24 million choose 2 minus 24 million, which is a huge number of off diagonal things. And in my experience, it's just easier to hide your mistakes in those off diagonals than it is to pull inside out. So you got to be really careful if you do that. So I think biasing towards a diagonal structure, when we're doing an iterative algorithm, if you were to do a one-off, that's different. But these other ones you're mentioning are not one-offs, right? They're iterative algorithms too. And so, yeah. So I think it's more robust in both fronts, and it achieves state of the art sort of out of the box. Whereas I don't think you can say that about the other ones, basically.
Thank you.
So are there any other questions from, okay, we have a lot more questions.
So I just had a question. Is there any application of second order optimization methods to robust scan training, which tends to be more sensitive to hyperparameters in general?
Yeah, I mean, I have a list of things to do right over here, and that's one of the ones to look at, because I suspect that there would be. Second order provides sort of a lot more structure and so yeah, so I don't know, but that's one of the things we've looked at, and I think the mental model of second order minus minus, I mean, would provide sort of a lot a lot less wiggle room to fiddle with your hyperparameters. And I suspect we've seen in other contexts that it does lead to more robust models or more well-posed models. And so I suspect it would do better there, but we haven't had a chance to look at that yet.
Yep.
So Haiying, you want to ask a question?
So how does Adahesian compare to other second-order methods like Newton's methods or variants of these methods?
I mean, what's Newton's method? So Newton's method is,
well, it's just taking advantage of second-order derivatives, and in our cases, the Hessian matrix.
Right. So vanilla Newton method is form a Hessian, solve a matrix equation, and which sort of in a sense is computing the inverse Hessian times the gradient. So you can't form the Hessian and you can't take the inverse.
Okay.
So those are off the table. If you wanted to do that, so the mental model is essentially we're coming up with a diagonal approximation to the Hessian.
Okay.
And so then, Newton's method doesn't have to be with the exact Hessian. I mean, the work with Fred Rooster, that was the way we got into this, looked at subsample Newton methods. And so subsample Newton methods decrease the cost of that linear equation solve. And in some cases, you can implement them in matrix-free ways. And most of the theory there that people have for Newton's method is basically, if I'm convex, I'm pretty smooth, I iterate, and I get second order convergence rate. I say most, I mean, Newton MR can work with a broader class of invex problems. So you don't need to be, you can have much weaker continuity, smoothness properties and be discontinuous. But that's still, if you think of solving linear equations versus min-res versions of linear equations, Newton methods to Newton MR, you can use Newton to find saddle points, but there you're still getting the full Hessian. So from that perspective, think of this as a diagonal approximation to the Hessian, computed without writing down the full Hessian. So using the Hutchinson and the randomized linear algebra techniques to approximate the Hessian. And then since that stochastic approximation injects a little bit of noise, use those other two methods to reduce the variance.
I also, so I don't quite understand how can we approximate a matrix with its diagonal? How do you deal with other non-diagonal entries?
Well, so why do you even care about the non-diagonal entries? Is the first question. So you never need the Hessian. What you need is information from the Hessian, and in particular, write it down on a piece of paper. What you want is the inverse of the Hessian times the gradient.
Okay.
And if you get the inverse of the Hessian times the gradient, that tells you a direction to move in. So we're saying don't write down the full inverse Hessian times the gradient. Write down essentially the inverse of a diagonal approximation to the Hessian times the gradient. And it's not quite that, it's that slightly more complicated formula we had, but think of it as that way. Now that, if this is the gradient direction, first order, and the inverse of the Hessian times the gradient is the points in this direction, we're pointing in this direction, right? So we're not pointing in either of those directions. But what we're saying is that we're pointing in a direction that's closer to the one we want. And then when we iterate, we can approach that faster. And we don't have to add lots and lots of hyperparameters in the first order method to get this close. But we may be losing something, and I'm sure you can find a worst case example where something happens, but for at least the state of the art ML and AI problems, those don't arise. But you never need the Hessian. You need the action of the Hessian or the inverse Hessian on a vector, typically the gradient.
Okay, thank you.
Yeah, so Aditya, do you want to ask more questions? I saw you raise your hand.
That is my.
Okay.
Hi. Yeah. Just one question. So, instead of approximating the Hessian by the diagonal and then inverting it, is it possible to approximate the diagonal of the Hessian inverse itself using any randomized method?
Yeah, but we actually feed that into that other expression, and I don't know that that would matter. you'd get a certain level of a theoretical statement, but I think that the way we'd use this isn't close enough to the theory that the differences between those two would matter, right? Because if you approximate one versus the other, are you asking for an additive error or a relative error on the diagonal elements? And I think there's the theory practice gap would be bigger than the distinction between what you're asking.
I see. Okay, thank you.
Thank you. So yeah, we have a few other questions in the Q&A. So Michael, can you see that? If you click the Q&A, there are, I think, 4 questions. Some of them have been answered, but I guess there are 2.
Can you read them? I can't find them here.
Okay. Yeah. So the first question is the computation of the Hessian to the power of minus k seems to be as expensive as the Hessian to the power of Hessian inverse. Is there any intuition that k between 0 and 1 helps the performance over k equal to 1?
Yeah, so the computation time is we never compute the Hessian inverse. I wouldn't even think of it. It would be insane to do. I wouldn't even form the Hessian. The Hessian is 24 million choose 2. I wouldn't even think of writing it down. What I need is the action of the Hessian on a vector, and we can get that. We can get a good approximation to that. And the amount of computational time it takes is 2 backprops. And I had that slide that showed you, in fact, it's not 2 backprops, it's less than that. You know, because you don't have to compute this every step, you can compute it every 5 steps, in which case the compute time is 1.2 backprop. So, I mean, and we could probably play games and make it not 20% more expensive than first order methods, we could make it 10% more than, you know, so that's a parameter you could fiddle with, right? But it's 10 or 20% more than first order computation. So it's marginally more expensive, and we get this information. And it takes the same amount of time to get, you know, k is a half, k is 1. I mean, that's the same amount of time, 10 or 20% more, right? Now, a separate question is, why do you want to choose k slightly less than 1? And the interpretation I gave, which I think is probably the right one, is it's a little like shrinkage, right? You know, we're not moving quite as aggressively in the, you know, because what the Hessian inverse is doing is, think of it, if the Hessian is U sigma U transpose, Hessian inverse is U sigma inverse U transpose, right? So you're rotating, you're stretching by something, and you're unrotating. And so we're just saying, you know, don't stretch quite as aggressively, stretch a little bit less. And so, you know, if the aspect ratio that you stretch and unstretch is 100, we're saying stretch and unstretch a factor of 50, and you'll compensate for that at the next step of the iteration. Does that make sense?
Yeah. Actually, we do have a work called a partially adaptive gradient method, where we also introduce a parameter similar to k here. And we also, by experiment, we found that if you choose k less than 1, empirically it works much better. And also in stereo, we can also deliver some theoretical justification to show that why k less than 1 is better than k equal to 1. And so I totally agree. Yeah, by choosing k less than 1 may give better performance. So there's another question: is the Hessian in deep learning essentially a diagonal matrix? So this is a question from a student.
You know, it's not diagonal. No, I mean you saw the picture of it. It had a lot of stuff off diagonal. So it's not at all diagonal. This is an approximation that you're using inside an iterative solver, but yeah, I don't think it's diagonal, because it's not.
I see. So I guess the question is,
if you have 24 million choose 2 parameters in your matrix, how many of those are quote real, and how many of those are just sort of noise? I mean, that's you know, so it's not diagonal. And if you saw that figure, some are, you know, that was color coded, grayscaled, or I think it was blue scaled. Some of those are larger, those are probably real. A lot of the smaller ones are probably noise. And so the question is, you know, is it easier to try and figure out which of those are real and which of those are noise and muck through the 24 million choose 2, or is it easier just to say, get the diagonal and iterate? And for some problems, you need to do the one, but for iterative solvers, you need to do the other.
I see. Yeah. So the last question in the Q&A is, how is the performance guaranteed by taking only the diagonal of the Hessian matrix? So I think it's about a theoretical guarantee about the convergence.
Yeah, so that's something else on our list of things to do. So we don't have in the current paper a statement of the theory. I'm sure I'm sure we could have come up with something under sort of implausibly unrealistic assumptions, something converges in the same way. We don't have a statement that says under sort of reasonably realistic assumptions, you're going to get something converging in the same way. And we've wondered a little bit about that. And I think it's a nice sort of open question or problem, right? Because what you want to do is to say, I'm close enough to what I would want in terms of the act. I mean, there's two places that could manifest itself. One is in the approximation at each step, and the other is how you chain them together during the iterative solver. So, I mean, so getting a not implausibly simplified set of assumptions under which you'd converge might be nice. But then the question is, where are you converging? Are you making some smoothness assumptions and you're doing convex optimization? I mean, that's good, but that's not what's going on here. So you could do a truss region and look for a saddle point, and that would be at least a little more aesthetically appealing than a convex. But the form of that theory is sort of similar also. So so I guess it really depends on, are you asking for that? That would be interesting. Or are you asking for sort of why it would perform well it does in these sort of ML applications, which would be something a little more challenging.
I see. Yeah, I think Michael has addressed all the questions. Are there any other questions from the audience? All right. So let's thank Michael again for the great talk. Thank you, Michael.
All right. Thanks a lot.
Mm-hmm.